In this video, we're going to learn about some common relations, or proportionalities as they're occasionally called, and the graphs that they produce. If you plot y against x and they're directly proportional, you get a straight line through the origin. If you plot y against x and y is proportional to the square of x, then the graph looks like this. One of the ways you can imagine or predict this graph is if y is proportional to the square of x, then instead of y right here, we could write a constant times x squared. So the y value should grow much more quickly, and so the graph should get steeper and steeper. Let's say we have a relationship where we plot y against x, and you have something like this. This type of graph is going to typically be a square root graph. Square root. And the reason we call it that is because y is proportional to something like the square root of x. So instead of plotting y right here, y is equal to a constant times the square root of x. So you can see that x is going to grow more quickly and y will grow more slowly, so the graph should get less steep. And then finally, we'll do two more. If y is proportional to the inverse of x, we call that inverse proportionality, then the graph will look something like this. And if y is proportional to the inverse of x squared, and you plot y against x, and again the relationship y is proportional to 1 over x squared, then the graph will look like this. Similar to the inverse shape, just it hugs the axes a little bit more closely. Now there's something important to note. If you have something like y is proportional to x cubed, then it'll just be the same basic shape, but a little bit steeper. If you have y proportional to x to the power of 1.5, it'll again be kind of the same thing, but just not quite as steep. And likewise, if you have y proportional not to the y proportional to x, not to the 0.5 power, but the 0.2 power, what do you have? Well, the graph just will level off more quickly. And likewise, if you have y proportional to x raised to the power of not 0.5, square root is 0.5, but let's say instead it's 0.8, then it'll level off more slowly. Right. Kind of how you have inverse and inverse square. This one is called inverse square. Are the same basic shape, but the difference is in how steep, how quickly they increase or decrease. Alright, on to the next page. Experiments have uncertainty. If you do an experiment and nothing goes wrong, even in that perfect experiment, the devices themselves introduce uncertainty. Why? Because devices can't measure every single place going on forever. Some decimal places have to be left off. The two types of devices are analog and digital. Digital have a screen that reads off the number, the measurement. So for example, a thermometer is often digital, and it'll just say 21.3 degrees Celsius. It tells you that measurement, you don't have to do any work to get it. Analog devices, though, require a bit more work. A device is analog if it has tick marks. An example is a ruler or meter stick, and another example is anything with a dial, where the dial swings back and forth between different tick marks. So a clock is an analog, an analog clock is a clock with a seconds hand and a minutes hand. There's a rule for analog devices. The smallest acceptable uncertainty is half of the smallest increment. So if two tick marks are separated by 0.01, if they're separated by 0.01 centimeters, then the smallest acceptable uncertainty for that analog device is half of 0.01, or plus or minus 0.005. Here's why we do it that way. Here's the rationale. Let's say you take this meter, this ruler, and you want to measure the size of a pea. Okay? So you get your pea, and you line it up, and there's my pea, the little green pea. I should make it green, shouldn't I? Remember, each tick mark is 0.01. You know that the pea is 0.01 something. You know it falls after this tick mark, right here, and you know it falls before that tick mark. So there's no way it could be 0.02, there's no way it could be 0, it's 0.01 something. So the measurement is 0.01, and then you estimate the next place. Let's say you think it's 0.013. How much could you be off? The smallest, the rule is you could at most be off around 0.005, half the tick mark. So we're not going to mess this up more than half of a tick mark. That's the thought. For digital devices, it's a different rule. If your device measures to the 10th place, like 21.3, that's the 10th place, then your uncertainty is automatically plus or minus 1 in the 10th place, so 1/10. If the device were to measure 21.33, your uncertainty would be 1 in the 1000th place, so plus or minus 0.01. So it's always 1 in the smallest or the last measured place. Now, things go wrong in experiments, which cause us to estimate the uncertainty to be higher than these rules, than what the rules dictate. So for example, if your vision is not very clear, or if maybe the pea has rounded edges, or maybe you're viewing from an angle, here you are, you're looking from an angle, here's your eye, and so you see that the pea is somewhere around 0.02 something, that's called parallax. Any of these sorts of things can cause you to estimate your uncertainty to be higher. So you say, well, there's no way my uncertainty is really this small. I'm going to estimate my uncertainty to be plus or minus 0.1 centimeters maybe, or 0.2, or whatever it might be. You can estimate it based on factors. In your experiments, in your labs, you're going to have to, in your internal assessment, you're going to have to estimate that uncertainty to be higher and justify. You'll have to say, was it clear vision? What was the reason why you chose a higher uncertainty than the device uncertainty? Okay. For digital devices, what sorts of things can cause us to estimate a higher value? Well, let's say you'd measure the temperature, and the temperature is 21.3 1 second, and then the very next second it jumps up to 21.8, and then it jumps down to 21.0. If there's fluctuation, but it should be a constant value, then that fluctuation can cause you to estimate the uncertainty to be higher. So you can talk about that in lab reports. Now let's say you have a problem like this. A digital thermometer has an uncertainty, has a measurement, or shows a measurement, of 5.0 degrees Celsius. Determine the absolute uncertainty in temperature to the 2.5 for this measurement of 5.0 degrees. Well, to find the absolute uncertainty, you need to know what the uncertainty is for the 5.0. The measurement is 5.0. They haven't specified an uncertainty, so you assume the smallest possible, the device uncertainty. Like that. So starting from there, find the absolute uncertainty in t to the 2.5. Go ahead and do that. Okay, vectors and scalars. We've learned about this. Scalars only have magnitude, a size, or an amount. Now the magnitude can be positive or negative. Temperature can be positive 51 degrees Fahrenheit, or it could be negative 20 degrees Fahrenheit. So simply having a negative does not mean it's a vector. Magnitudes can be below 0. You can have negative magnitude. Work is the exact same way. Work is a scalar, but you can do negative work. Okay, vectors on the other hand, so scalars have magnitude only, no direction. Vectors have magnitude and they have direction. So to the left, to the right, up, down. In the case of a one-dimensional vector, one-dimensional means just along a single axis, so just the x-axis, just along the y-axis. For vectors that are pointing along one axis, you can use positive or negative to represent the sign. To represent the direction. Usually we say right is positive, left is negative, up is positive, down is negative. Here are some, now vectors of course we draw with arrows, because arrows have a magnitude, a length, and they have a direction, a particular way they point. Here are some examples of scalars and vectors. This one I want to point out, field strengths, we're going to learn about this. Gravitational field strength, you can write the whole word out. That's a vector. We're going to learn about another example, magnetic field strength. You can write out the whole word magnetic. And another field strength we're going to learn about is electric field strength, which we've already seen some of last year. Okay. By contrast, here are some scalars to know. All types of energy, that includes kinetic and potential. None of these on the left have direction. All of these on the right have a direction, like to the right, up, down. We know how to add vectors graphically. Graphically means adding them tip to tail using a picture. So for example, here is vector A. Here is vector B. Oops, I should use a different color for A. And let's make a purple as well. No, let's make it red. How do I add A plus B? How do I get the vector sum? Well, I take A, I connect it tip to tail with B, so the tip of A connects to the tail of B. Right? There's the tip of A, there's the tail of B, they're touching. And then I draw the resultant from the very beginning to the very end. The resultant is just the vector sum, the sum of the two. So adding A and B means connect tip to tail, but the vector sum, the resultant, you'll notice, is not tip to tail. The vector sum is tail to tail and tip to tip, so it follows a different rule. So I'd like you to take some time, practice, try drawing these three vectors added tip to tail. Do that for 1 through 4, and then we're going to take a look at vector subtraction. Okay, there are two ways to do vector subtraction. We've done vector addition. Here's the shortcut way. You want to do VF minus VI, so you connect the two tail to tail. It's a little different. Here's VI, here's VF. And then, if you're doing VF minus VI, then you draw your arrow the opposite way. And green shows VF minus VI. By the way, final minus initial, that's delta V. So the green here is delta V. So if you're doing final minus initial, then you go the other way with your delta arrow. Why does this work? What's the trick here? Well, let me show you. Instead of thinking about the vector subtraction, I want you to rearrange this equation so that you're looking at a vector addition. How do we make this an addition? Add VI to both sides. And then it shows VF is VI plus delta V. So VI and delta V, those are the ones being added. Those are the ones we add tip to tail. So you draw your green, you draw delta V, so it connects tip to tail with VI. What's the resultant? VF. So you draw delta V, so it connects tip to tip with VF, the way resultants connect tip to tip. And also this explains why at the beginning we started by connecting these tail to tail, because VF is actually the resultant. Okay, let's try one more. You've got initial and final position, and you want to find the displacement delta r, which is final minus initial. So to subtract one vector from another, this is how we do subtraction. You connect the two tail to tail, and they already are done. That's done. They're already connected tail to tail in the picture. And we want to draw final minus initial, so we start our vector, our missing vector, at the other end and do the opposite. Go from initial to final. and that is delta r. That's final minus initial right there. How do I know? Well, if I rewrite this to show the addition, I should add r initial to both sides. Now I see r final is the resultant, so it should be tail to tail. Yes, it is. It should be tip to tip. Yes, it is. Whoops. It should be tip to tip up at top, tail to tail at the bottom. And delta r is being added tip to tail with r initial, just like this shows. Okay. The other way to do vector subtraction, here's the other way. You've got two vectors, r initial, r final, and you want to do, in this problem, find r final minus r initial. Here's r final, and I'm going to draw negative r initial. To make r initial negative, I just put the arrow tip at the other end. Okay? And now, I'm going to do delta r equals r final plus negative r initial. So my red line here is negative r initial. My blue line is r final. And I have to connect those two tip to tail, because the equation here says connect r final and negative r initial tip to tail. So let me connect these tip to tail. R final, and then I connect r initial, or it doesn't matter what order you do it in. So the resultant, in this case, delta r, is like that. Voila. There's your resultant. And when I say resultant, I mean the resultant of r final and negative r initial. So now take a moment to do numbers 2 through 6.